make sense of acceleration as it's related to speed in a very general sense. Let's look at how velocity time graphs can help us interpret data. I want you to be extra cautious about reading the axes titles, as a velocity time graph is interpreted much differently than a position time graph. We should quickly review some definitions so that we are on the same page. Acceleration is a vector quantity that describes the rate of change velocity per unit of time. Velocity is a vector quantity that describes the change in position per unit of time. Displacement is a vector quantity describing a change in position. Speed is a scalar quantity which describes the rate of movement over time. And finally, distance is a scalar quantity that is a measurement. I am going to assume that you have watched and understood the videos about position time graphs. I will be building on that knowledge. In class, we looked at how acceleration is framed in your day-to-day existence. But be that the acceleration of a vehicle, or acceleration of gravity, like skydiving, something like that. We've begun to explore what those look like graphically, but let's dive a little deeper. No pun intended. Acceleration is the slope function of a graph of velocity and time. Pow! Mind blown. Nah, not really. I know you guys knew what I was talking about, and that math theme just keeps cropping up. Darn those math teachers. So slope is rise over run, which is, in this case, velocity over time, or change in velocity over change in time. And it looks something like this. Look familiar? Something like this. It'll be more accurate. It's not quite the same as uniform motion, as we are dealing with different units. If you compare a PT graph and a VT graph, you should notice some pretty significant differences in labeling. The velocity is measured in SI meters per second, and position is measured in meters. Time is always time, and we see that in both graphs. And it's measured in seconds. So what, right? Well, the slope of the PT graph gives us meters over seconds, or velocity. And the VT graph gives us meters per second over seconds, or acceleration. Remember, that can be represented as meters per second, or as meters per second squared. So what does acceleration actually look like graphically? Take a car's acceleration from 0 to 28 meters per second, about 100 kilometers an hour. For fun, we'll make this an Aston Martin. The 2008 model could do that in about 6.3 seconds. Here's what the graph would look like. Our independent axis is time, and our dependent axis is velocity. I have averaged out the acceleration, so the graph is a straight line in the positive direction. So what does this mean? It means that the car was accelerating in the positive at 4.4 meters per second squared. Here's the calculation. First, rise over run is VF minus VI divided by TF minus TI, which as a formula is written as A equals delta V over delta T. If we plug the numbers in for final velocity subtract initial velocity over final time minus initial time, it looks something like this. When we use the order of operations and solve the equation like this, the Aston Martin is in fact accelerating at 4.4 meters per second squared. Okay, now let's look at the slope of lines and what they mean in terms of acceleration. A positive slope line means that the object is accelerating in the positive direction. How is that related to velocity? This animation shows 3 cars. Okay, watch it carefully. You might have to watch it twice. You'll notice that one of them is going at the same speed the whole time, and the other 2 look kind of like they might be accelerating. So how do uniform motion and acceleration compare? Have a look at this graph. Okay, let's break it down even further. Constant positive velocity looks like this. The blue dot moves at the same rate forward, the uniform motion we are used to. So, look at the graphs. The position time graph looks like what we are used to, a straight line headed in the positive direction. If we graph velocity time, like this, it's a straight flat line. Wait a minute, doesn't a flat line mean stop? This is where interpreting graphs becomes important. This is a velocity versus time graph, not a position versus time graph. The velocity is remaining constant but positive at about 12 meters per second. That gives it a flat horizontal line. There is a change in velocity, there is no change in velocity, so the acceleration in the third part of the graph is 0. Constant negative velocity looks similar, but you will notice that the position time graph has a negative slope line, and the velocity time graph still has that flat horizontal line, but it's in the negative. What does it look like if we add an actual change in velocity? This is a positive velocity, positive acceleration experiment. Notice that the position time graph is no longer linear. It's now curved. That is because as the object accelerates, it begins to cover more distance in time. Look at the velocity time graph. It has a positive slope showing that velocity is changing in the positive direction. The acceleration graph is no longer 0. It shows a constant acceleration of 2 meters per second per second. That means each second the dot speeds up by another 2 meters per second. What does it look like if I keep the positive velocity but add a negative acceleration? I'm effectively putting on the brakes. Notice that the dot is slowing down. Look at the position time graph. It shows a curve leveling off effect. This is because over time the dot starts to slow down, covering less ground per unit of time. The velocity time graph shows that linear change in velocity in the negative slope line. The acceleration graph shows a flat line, but it is now in the negative, showing the dot was slowing down by 2 meters per second every second. Do you think we can expect the same kind of thing if we have negative velocity and negative acceleration? Or do they do something different? Let's check it out. This is negative velocity combined with negative acceleration. Negative acceleration is not always putting on the brakes. Look at the position time. It shows you the dot is in fact covering more ground each second, just in the negative. Very tricky. The velocity time graph shows a linear negative slope line, and the acceleration graph shows that the dot is in fact accelerating in the negative at negative 2 meters per second per second. So what happens if we have a negative velocity and a positive acceleration? So this dot is moving in the negative direction, and we slow it down, which is a positive acceleration in this case. What? I can put positive acceleration and it means I'm putting on the brakes? Mind blown again. Look at the graphs. The position time graph shows a leveling off because of where we put the brakes on. The velocity time graph shows a positive slope towards 0, heading for a stop. And the acceleration graph shows a positive acceleration of almost 2 meters per second per second. I guess the red barn really does matter. If I were to put the last graph that I just showed you into a real life situation, this is what it might look like. A car heading straight back toward the red barn, putting the brakes on the whole time so it doesn't hit the red barn. It is accelerating in the positive because of where the red barn is relative to the car. I know that seems wrong, but the red barn has the reference as a reference point makes the directional information. Like this. You can see we're headed back towards the red barn. If I draw the scenario from the side, it would look something like this. The red barn is the reference point. Positive is to the right of the barn. If I place the car on the right of the barn and it moves back towards the barn, the velocity becomes negative. In order to stop the car before it hits the broadside of a barn, bad pun intended, you must apply a positive acceleration in the form of the brakes. The positive, negative thing is all because of the vector quantity taking into account the reference point. And Jones's big finish? These are the VT graphs of an object, moving with positive velocity. Notice one graph has negative acceleration and one has positive acceleration. These are objects speeding up and slowing down. The graph on the left shows the object speeding up with a positive acceleration on top and the object speeding up with a negative acceleration on the bottom. The graph on the right shows an object slowing down and a negative acceleration on top and a positive acceleration on the bottom. In short, putting on the brakes doesn't mean it's negative.